So matrix multiplication is defined using dot products. So we just want to take a quick moment to remind ourselves how to calculate a dot product. So in previous classes, dot product should have been defined to you. If we have a two-dimensional vector u and a two-dimensional vector v, in other words, each vector has two components, u sub 1, u sub 2, and v sub 1, v sub 2, the dot product, u dot v, is just defined to be the sum of the products of corresponding vector elements. So you multiply u1 times v1 plus u2 times v2. And that definition for the dot product in two-dimensional space extends into three-dimensional vectors, vectors that have 1, 2, 3 vector components. The definition still says to take the dot product, u dot v, take the sum of the products of corresponding vector elements, u1 times v1 plus u2 times v2 plus u3 times v3. And we can extend this into n-dimensional space where we have vectors with n components. We still define it to be the sum of the products of corresponding vector elements. So the key is that the way that dot product has been defined, you can only take the dot product of vectors if they are the same dimension. You can't take the dot product of a two-dimensional, for example, and a five-dimensional vector. So just to quickly run through a couple of examples, it says for each pair of vectors, calculate their dot products. So the first one, we have u and v. U is the vector negative 2, 3. This is a two-dimensional vector because it has two vector components. And the vector v is the vector 4, 5, which is also two-dimensional vector because it has two components. And because they have the same dimension, we can calculate their dot product. U dot v is just equal to the vector negative 2, 3 dotted with the vector 4, 5. And based on the definition of dot product, we take the product of corresponding elements. So we get negative 2 times 4 plus, take the product of corresponding elements, 3 times 5. So we get negative 8 plus 15, which is going to be 7. Here we have the vector r, which is negative 1, 2, negative 2, and the vector s, which is 2, negative 2, 3. When a vector is written in this form, this is the form of a row vector. It's written horizontally. And when it's written like this as a column, it's referred to as a column vector. And we're going to need both row and column vectors when we calculate the product of two matrices. So even though they're aligned differently, one is horizontally aligned, one's vertically aligned, we can still take their dot product because they're both three-dimensional vectors. They each have three components. So r dot s is just equal to the vector negative 1, 2, negative 2 dotted with the column vector 2, negative 2, 3. Again, we take the sum of the product of corresponding elements. So element 1 times element 1, negative 1 times 2, plus the second element 2 times the second element of the column vector is negative 2, so we get 2 times negative 2, plus, and now we take the product of the third components of each vector, so we get negative 2 times positive 3. It's going to equal negative 2 minus 4 minus 6, which is going to be equal to negative 12. Here, if we try to calculate q dot s, what we will discover is that this dot product does not exist because this vector is a two-dimensional vector and this vector is a three-dimensional vector. Because they don't have the same dimension, we cannot take their dot product.